Yes, hi. My name is Sebastian Pütz. I'm a PhD student from the Osnabrück University, and I am going to introduce tools for storing, rendering, and annotating triangle meshes in ROS and ROS. And I did that work together with Thomas Wiemann and also a master student project group, mainly in the last year. And Thomas and we focus a lot on mesh representations and the research in that in robotics. So coming from a point cloud, a high resolution point cloud, or many point clouds registered to each other, we can reconstruct these using, for example, the Las Vegas reconstruction toolkit, namely LVR, and then using the margin cube approach, and then reconstruct it to a mesh we see in the video, and then also retessellate the triangles to reduce the data, and later also applying some textures so to keep the color information we will see now. So, and now our idea was bringing that to the ROS world, because I think there are many applications for ROS dealing with meshes. And why should we do that? So the advantages of meshes are, for example, 3D mapping in outdoor terrain, and in contrast to other map representations, we obtain directly the surface information, and they are also suitable to represent multi-level environment and also multi-story environment, like multi-story buildings. If we think about parking garages or underpasses, we can do that directly with meshes. And also, if we see that picture, the visualization of terrain analysis, like height differences or roughness, is straightforward. And we will see that in a minute in an example used for robot mesh navigation planning, where we fuse these levels or layers to one layer where we then navigate on. And as I showed you in the video, it's possible to visualize textures directly on the mesh to keep information like we got from a camera or even a hyperspectral camera. We will see that in the end of the talk. And as I said, we can reduce data fitting planes into the model. And it's like quite intuitive for humans to annotate objects so that we get semantic information in the 3D world. That's not possible, for example, for 2.5D maps or something like that. So what we brought to you is like some packages, starting with mesh messages. We define some messages for the geometric structure, as well as like the analysis and metrics we can apply on the meshes. So of course we also provide a package for transforming meshes from one coordinate system into another coordinate system, or from one frame into another frame. And we also provide to make it persistent, because we're sometimes dealing with really huge data sets up to 100 or 200 gigabytes. We use like persistent layer using HDF5. Thereby we present mesh message HDF5 package and also HDF5 map.io to make it directly without the step over the messages. And also we provide a label manager. As I said, we want to label maybe objects or something and get the semantic information from that and store it. And to make it visible and to show all the meshes and their attributes, we present here two plugins for ROS, namely the ROS Mesh plugin and the ROS Map plugin. The Map plugin is directly speaking to the HDF5 layer to make persistence, so save and load data. And it also has a pipeline for annotating objects. Starting with the geometry, we defined a mesh geometry message. And of course, like it's traditional in computer graphics, we have a vertex buffer and an index buffer. So every 3 entries in the index buffer point to vertices in the vertex buffer and thereby define a face. And optionally, we can also provide vertex normals. We will see that also in a minute in the video. And of course, we provide a stamped version. And as you can see here, here's also provided a UUID to make it possible to refer like other metrics like cost values or something like that to that mesh. You can imagine if we have a really huge mesh, we don't want to send it all the time, just once, and then some pipelines can process on that and send the rest after they are finished. So here you see the ROS plugin just showing the geometric structure of a typical outdoor environment, a bit rough. So it's just a small part showing how it works. We can change the color, and we also can make it more transparent, set the alpha value. And we have also the possibility to show the wireframe, and you will see that mesh is quite detailed. And I talked about vertex normals, and we can display these two here. And also change the color if we want to, just for introspecting if all worked and our nodes did the right thing, and maybe the normals were not computed rightly. Going one step further, we want to introduce like costs and colors for these meshes, and they are then refer to a mesh using the UUID, as I said, and that's just a float array or vector, and has the same length as the vertex buffer. So on the right side, you see we did that for the Ford Campus data set and labeled some object there, and yeah, before we reconstructed that. And now I want to give you an application. We work also using move-based flex. So mesh navigation is working like we first reconstruct a point cloud to a mesh, and then doing terrain analysis on that, computing cost layers like height differences, roughness, riskiness, maybe also including some semantic information, and then fusing that together to a navigation layer. And on that, we can perform path planning and even motion control. And yes, I said, so that is also published 2 years ago, 3D mesh navigation generation for path planning in uneven terrain. And as I said, we have a move-based flex navigation server for that, since move-based flex is map representation independent in general. So also we released a new version of move-based flex, I want to say, 2 weeks ago or 1 week ago, and now it's possible to plan in parallel. And also I give a talk on Wednesday on the ROS. There we show how move-based flex boosts performance on Magazino robots versus the old move-base, and we prove that with numbers. So you're welcome to visit. So now we see the terrain analysis. So that's the mesh again we used before. And then we want to show the vertex costs. Like here's selecting the roughness. And we are also able to change custom limits. So that makes it really intuitive to define thresholds for a certain robot. So we can say, okay, that robot is not possible to deal with these kinds of obstacles. Or though we even see that the height differences is computed correctly, and we can change between the layer and also disable the wireframe. And we then have also a riskiness layer we will see in a second, which combines the layers before and also inflates these dangerous areas. So we can perform then path planning and navigation on that. So also we provide a tool for selecting a pose onto on the surface of the mesh, and then move-based flex got that pose and is computing a path. And we also can then display the potential field for that. And you can imagine like a local planner or a controller is using that potential field. Okay, going to the next topic, like labeling. We see on the right side a door is labeled, and this is a mesh with textures, and also the floor is labeled in a different color. And so therefore we defined also some messages, like a number of face indices we have selected, and an optional label. And of course, referring to a mesh using the UUID and a header. Now we want to apply some textures. Therefore we defined mesh textures, and like having a UUID referring to the mesh, and a texture index. So we define a texture index and also in an image, and then later, or traditionally, we have something like a material, and a material can then refer to a mesh texture or have a color. So, and then we have mesh vertex text chords, which are referring to a certain pixel in the image, and then referring with mesh materials referring to a certain vertex of a face. So we want to store these data. So you can imagine if we have a lot of materials and a lot of images and millions of points, then it's like hard to store that with ROS bags or something like that. So we thought maybe hierarchical data format 5 is a good idea, because it's used widely in the scientific world, and it's made for complex structures and metadata, and also it's a portable format. So on the right side you see our structure we use here. We have attributes like height differences, the normals, RGB colors, roughness, and so on. And of course geometry, then later labels, and also the textures. And we now see like a short video or a bit longer video where we applied textures which were generated by a hyperspectral camera. Like we mounted a hyperspectral camera line camera on a laser scanner and assembled these then. And At the bottom, you find the paper where we do the registration between the hyperspectral image or hyperspectral data and the laser scan data. Here we see a bit bigger data set, which was directly loaded using the HDF5 persistence package. And we see the wireframe, so you can see some trees and so on, and the pathway. So this is a typical outdoor rough terrain environment for our use cases, for navigation and so on, and where we have collected some hyperspectral information, and these hyperspectral information are starting from 400 nanometers wavelengths up to 1,000 nanometers wavelengths. So, and these colors are fake colors, like some certain spectral channels, and then computed to RGB. So you see, this is possible with the mesh tools right now. And you could then simply save and load these data. And these data sets, as I said, can be really huge, like up to 100, 200, 300 gigabytes, depending on the resolution and how many channels you like have in your hyperspectral information. Okay, thank you. Please download and test and contribute and write some issues. Have you any questions? I hope so.
So as you said, the data sets can be quite large. Are you doing any sort of like paging or level of detail in RViz to handle that? How does it perform with these large meshes?
Not yet, but yes, we also deal with out-of-core algorithms for doing that, especially chunking is a problem. And yes, like a voxel kind of resolution is planned, but not yet implemented.
First off, this looks great. Thank you so much. You did some terrain analysis for positive obstacles. Do you do any terrain analysis for negative obstacles or holes in the ground?
Yes, this would work because it's like not depending on if it's going to the positive side or to the negative side. And you could also implement some other analysis and yeah, then analyze if it's doing the right thing or not using some color sheets.
Okay, thank you.
Thank you very much, Sebastian.